So here we are. All right, so homework 2 is posted. It's due on Wednesday next week, 1 week from now. Again on Gradescope. And please, when you submit your homework on Gradescope, submit your answers question by question. You can choose which part of your homework corresponds to which question. This helps very much in grading. So after this unit, you will have the first in-class test, and which will be held inshallah on the, I think, 5th of October. So next week you submit the homework, then you see the solution, then you have some time to study, and then about 10 days after that you will get the first in-class test. All right. Yes, and after the mechanical systems homework, there will be a new homework on electrical systems. So after you submit all homework, you will be tested. Okay, so you will have some time to see the solution and study for the in-class test, which is worth 10% of your final score for the course. Okay, any questions about that? All right, if there are no questions, so we will proceed with the material. So there is another handout 2, on modeling electrical systems, which is posted to the Blackboard. So the learning objective here is really something similar to what we did for mechanical systems. So it's to derive mathematical models, ODE models, or transfer functions. We'll talk about that later, of simple electric circuits involving resistors, capacitors, inductors, current sources, and voltage sources. So again, if I have a current element, a circuit element, then the current that goes in is the same as the current that goes out. So I1 is really the same as I2. Very well-known fact. So we only show one of them because we don't need to show the other. And the direction of the current is really the direction of movement of positive ions entering the element, and the electrons move in the opposite direction of the indicated current direction. So now we remove I2 because we don't need to show it. The next thing is really the resistor. So we have elements. So similar to what we did for mechanical systems, we talked about springs, dashpots, friction, things like that. We'll talk about resistors, capacitors, inductors, and we will use Kirchhoff's laws to really to really build the relationships among these elements, similar to what we did to the mechanical systems, where we use Newton's laws and also D'Alembert's law. Okay, so the resistance of a body of length L and cross-sectional area A with resistivity factor rho is really just rho L over A. So rho R here is usually given. This is just to give you the physics-based definition. And we have Ohm's law, E equal Ri. E here is the voltage. So we denote the voltage by E in this course. So I is really just E over R. Next, we move to the capacitor. So the capacitance of two parallel metallic plates with area A separated by a dielectric material of thickness D, and permittivity epsilon is really epsilon A over D, and the unit is farad. So again, it's like resistance. We take this as a fixed parameter, and sometimes we give you a value for it. So, but again, we need to show the physics-based definition just to get a clearer picture. So we have a linear capacitor module. So I, the current through the capacitor, is C dE dt. So E is the voltage. So notice here that we're having derivatives, right? So this is why we have differential equations. This is how we get, because these derivatives really capture the dynamics of the circuit, and we're interested to study how the voltage, let's say, vary with time, because you might have an input voltage and you wanted an desired output voltage. Really, if you're doing control, your input to the system is most likely a voltage. So if you set a thermostat or let's set like let's say a speed for a cruise control in your car, you really set a number, and that number goes through a circuit, and that has a corresponding voltage. And then that affects the system, and there is an output voltage that's coming from the sensor, which captures the actual speed of the vehicle. So we need to cover all of these relationships. So voltages, currents, all of these matter a lot. And the resistors, capacitors, all of these elements might represent other elements in the car. So since we have a derivative here, represent the voltage E at time t, then it's really the initial voltage plus 1 over c, the integral of I from t naught, the initial time, to the final time, or the time we're interested in, t. So what I did here is really just I integrated both sides and moved c to the denominator of the other side. Similarly, we have inductors. So inductors is really, so basically if you have n turns of wire of a toroidal core of a material with permeability mu, cross-sectional area A, and mean circumference L, then we have an inductance formula, which is measured by Henry. Again, an inductor will have a certain differential equation. Notice that this differential equation is really in terms of I. So the voltage across the inductor is really L E dot or L E prime. So it's the inductance, which is the number that multiplied by the derivative of the current through the inductor. So now we capture the dynamics of the current through the inductor. So similarly, if I divide by L and take the integral of both sides, the current at time t, the current through the inductor at time t is really the current at time t naught plus 1 over L, the integral of the voltage across the inductor. Because we care about things that vary with time, we have all of these derivatives that capture the dynamics of the system, and we need to study these relationships. And later on, we will see how to solve these differential equations. But the purpose of this unit is to come up with a model for a specific circuit. Then we have other element laws. For example, if I have sources, then I can have a current source, and the specific current is produced independent of the required voltage. If I have a voltage source, the specific voltage is produced independent of the required current, and here how we show them. Then we have interaction laws. Interaction laws describe the way different elements are interconnected, and there are two main important interaction laws: Kirchhoff's current law and Kirchhoff's voltage law. We will mainly use the current law in this course because it's the one that is, for the kinds of problems that we deal with, this is the one that helps us the most. Any questions so far? Comments? Okay. So for Kirchhoff's current law, the algebraic sum of all currents at any node is 0. So I1 is equal to I2 plus I3, or I1 minus I2 minus I3 is equal to 0. Also, some applications of KCL, if I have an element here, right? So why is it that the current through the resistor is the same? N is the same as R, because you can deal with the resistor, let's say, as a node. So the current that goes in by Kirchhoff's current law is the same as the current that goes out. It's one current, so there is nothing else that's going on. So this is one application. The current through the capacitor is the same as the current through the resistor, because I can have a node here and something goes in, it must be the thing that goes out. Similarly, I can have a node here, whatever comes out of the resistor will go to the next element. The current through the capacitor is the sum of the current through the two resistors in this case, because the current that comes in here must be split across the resistors and travel through the resistors. So you need to sum them up in order for them to be equal to the one through the capacitor. All right, we have also Kirchhoff's voltage law. So the algebraic sum of voltages across all elements that make up a loop is zero. So minus EI plus ER plus EC is zero. Minus EC, sorry. You know all of these things, so there is nothing new. It's just a quick refresher. An application of KVL is that the voltage across a capacitor is the same as the voltage across the resistor in parallel. Why? Because if I take a loop here, then minus EC plus ER is zero. So it must be that ER is equal to EC. This is why voltages in parallel are equal. And this is also why currents of elements in series are also equal. It's due to using KVL and KCL. So let me have recap on the element laws again. So we have a resistor with Ohm's law being the voltage is equal to Ri. We have also the capacitor, and the current through the capacitor is C, the derivative of the voltage. So if I manipulate things, if I want to, let's say, represent the voltage, then it's the initial voltage plus 1 over C, the integral of the current, through the time that I care about, from the initial and up to that point that I care about. Similarly, for the inductor, the voltage across the inductor is L, the inductance, di dt. So if I take the integral of both sides and rearrange, then the inductance, the current at time t is the initial current plus 1 over L integral of the voltage across the time that we care about, from t naught to t. So now we have all of these, we have the interaction laws, and we also have the element laws. So if I want to use KVL, then to obtain a model, I have to label loop currents, express the current through all elements in terms of one or more loop currents, and then use KVL and elements laws to write the model, to write the input-output relationship, because you have a corresponding voltage somewhere that is the input voltage, and you have a corresponding voltage somewhere that is the output voltage, which is, let's say, the load of the circuit. The other method is to use KCL. How to do that is simply label all voltage nodes. So if I have some circuits, like with some elements, I might have some nodes, right? So I label the nodes, then express the voltage across all elements in terms of node voltages, and then use KCL and elements law to write the model. This is the third model in this course. I advise you to stick to it. You can still use KVL or mesh, whatever, but really this is the one that will be most useful for control problems that we address in this course. And the reason is if you use KVL, sometimes you have to invent fictitious voltages, and then you have to deal with a larger model. So for the purpose of this course, if you just use KCL, you'll be just fine. So let us go through an example. Before I go through the example, do you have any questions? All right. So if I have an input EI and an output E naught, I want to build a model to represent the input-output relationship. Do that. Let me go to the steps. Label all voltage nodes. This is step one. How many voltage nodes do we have? I'm waiting for an answer. Yes, Muhammad.
2.
Where are they?
Isn't it?
Where are they? Tell me. Let's see. Where do you see the 2? Can you identify the locations of the nodes that we care about? Okay. Can you answer now? Yes, Muhammad. Keep going.
علق علي معلش طلعني ورجعني.
ما عندك مشكلة.
أتوقع 2
Okay, وينهم؟
EI و E0.
Okay, this is the input and this is the output. We're trying to build a relationship between the input and output. So I want a system of equations that is only a function of the input and output and their corresponding derivatives. So to do that, I cannot do this immediately. I need to use KCL, let's say. And we need, in the first step, we need to label the voltage nodes. So yeah, technically this is a node, but we have other nodes in the system that represent the input-output relationship so that we can capture them, right? Faisal, 6, where are the 6? You mean here, 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 here? Yes, Mazel.
And these are nodes.
3.
Okay, 3. What are the 3 that you're thinking about?
Yeah, one between R1 and R2 at the top.
Okay, okay.
One to the right side of R2.
You have one here, one here.
Yes. And one is with the ground.
Correct. Right, this is the reference node. So we do have, yes, Muhammad, do you want to add something?
دكتور you mean الفولتج source ولا nodes؟
I said nodes.
اوه انا معلش صح اجل
Yeah,
فعلا
yeah.
4 اللي هم هذيل اللي قالهم ايه.
It's actually have 3. Why? Because you have one here, and the voltage here is the same, right? So it's one node. And you have also the ground, right? So the voltage at this node is really the output voltage. And we have a voltage here between R1 and R2 AA. And we have the ground. So now we take every node and we try to identify. So what is the next step? Express voltages, express voltage across all elements in terms of node voltages. Okay, we did that. We will do that now. And then we use the element laws. So we have, okay. So what we have is that we have the voltage through the resistor here, which is EA minus EI, right? This is the voltage across the resistor. The voltage across the capacitor is simply EA. The voltage across the resistor 2 is EA minus E naught. And then the voltage here is just E naught across R3, similarly for C2, similarly for L. This is the second step. We just represent the voltage across every element in the circuit. And with that, we are ready to apply KCL. So at EA, we have, let's say, we have 2 equations. One corresponds to this node and one corresponds to the output node, right? So for the first one, what is the current? So we have a current here, right? And the current here, the current here. So what is the current through R1? Yes, Mazen?
EA minus EI over R1.
Yes, EA minus EI over R1. Okay, what else do we need? So this current, what else do we need? Yes, Abdullah.
EA minus E0 over R2.
Okay, so do we have a minus or a positive sign here? So we have this, we consider this one, and we have another one, right? EA minus E naught. So we use it the same, or do we have a negative sign over it? Yes, Mazen.
Plus EA
Okay, why?
because it is from node EA to the ground.
Okay, so we have EA minus E naught over R2. I'm referring to this one, sorry.
My mistake.
Okay, no problem. So you can talk about the current through the capacitor. What is it?
It is EA.
Just EA? Is this E is a voltage? We want the current. We're studying the node here. The sum of all nodes going out is 0, right? So what is the current through the capacitor? Can somebody help me? I'm waiting for an answer. Yes, Abdul Wahab.
C times EA.
C times EA,
Yes.
like this. Is this the current?
Or the derivative of EA.
CEA dot. Okay.
Yes.
Yes, Mazen.
If I'm not mistaken, it is the integration.
Okay, so what is the other what is the other candidate that you have in mind?
It is E of T0 plus 1 over C integration from T0 to T of E of T, E of X dx.
E of X or E of A? EA of
EA,
X.
EA, I mean, yeah, EA of X
Okay.
dx.
Okay, let me take a vote here. This is the first choice, 1. This is the second choice, 2. 1, 2. Please vote. If you don't know, do not vote. If you have a guess, vote, because if you don't know, then your vote will be just a guess, so it doesn't have a meaning. So we need to see the difference. Okay, so we have 5 versus 4. Let me wait a little bit. Okay, it's a tie, 5-5. Let's go back. The current through the resistor, through the capacitor is C dE dt. The voltage itself is E T naught plus 1 over C, the integral of I. Okay. So this is actually Even if it's the other one, it's also wrong because this is an integral of I. So we will erase what's not correct. Okay, do I need anything else? We have all current, so we don't need anything else. So this is just really 0. Okay. Now we have the other node here. So we have the current through R2. Or maybe, you know what, let me just use the same direction here. So we have this current from R2, the same one, is equal to the current through the inductor plus the current through the capacitor plus the current through R3. So equation 2 simply says we have EA minus E naught over R2. So I'll highlight this in green because it's a common element between the two circuits. Or let's say cayenne. So we have these two. Notice that because I have two nodes, I have two equations. So with that, I can build relationships between the input and the output, right? So I have EA here, right? But if I can, let's say, have two equations, then that will help me build a deeper relationship between or direct relationship between the input and the output voltage. Okay. So this is equal to what? This is equal to, what is the current through the inductor? First of all, any objections about this move? Do you agree? If you don't agree, tell me. So we have a current through the inductor here. Okay. So what is the current through the inductor? Yes, Mazen.
E نوت على R3.
Is this the current through the inductor? This is the inductor.
لا لا
This
لا
is the
لا
resistance.
لا لا لا.
Okay, this is the current through the resistor. Okay, this one is. Okay, covered. So we need two more. We need a current through the capacitor. Okay, what is the current through the capacitor C2? Using the same formula which we use for C1, it is C2 E naught dot prime. Okay. Now, what is the current through the inductor? Can somebody help me? Yes, Yasser.
Is it the integration of E naught?
Okay, just the integral, or we need more elements? Yes, Mazen.
It will be I of T naught plus 1 over L.
T naught plus
1 over L. Integration from T naught to T.
Okay.
E naught X dx.
Okay, any other opinions? We can verify, go back. The current through the inductor is equal to the initial current plus 1 over L, the voltage across it. So this is actually correct. All right. Okay. Now, you did not get the second equation. Okay, good. So we have a question. Okay. So we have to sum all, so the current through R2 is the same as this one plus this one plus this one. The current through R2 is simply EA, the voltage here, minus the voltage here, E naught over R2. This is equal to the current through the inductor plus the current through the capacitor plus the current through R3. We will start from R3. The current here is simply the voltage E naught over R3 plus the current through the capacitor C2. It is C naught E naught, C2 E naught prime. Why? If I go to the element laws here, this is the current formula. If I have a capacitor, the current is simply the capacitance multiplied by the derivative of the voltage across the capacitor. Also, if I have an inductor, the current through it is simply the initial current over L integral of the voltage. If we use these two formulas, then we have, this is the current through the capacitor, and then we have the current through the inductor, which is the current at time t0 plus 1 over L, the integral from t0 to t, E naught of x dx. Notice, why do we have t0, t, and all of these? Because voltages and currents are all functions of time, and we're capturing the dynamics. Notice that we have here the voltage is you have a derivative, so you need an initial time. So call it t naught. Usually we take it to be 0, and then we compute. Okay, Muhammad, is this clear?
Yes, and very clear. Yes. Thank you.
Okay, good. All right, so I'm going to remove everything and I'll ask you guys to solve it on your own. I'll give you 3 minutes. Yes, Mazen.
Sorry, doctor. We solve what?
You solved the exact same example. I just want you to practice it a little bit. Make sure
This
that you
example?
understand. Yes.
But I think we found the solution by the equations or what?
Yeah, but I
I'm not
removed it
sure.
from the screen, so you have to.
Okay. Okay.
Yeah, this is just to make sure if somebody there is something that's not clear, he gets a chance to check it and try it on his own. Yes, Faisal.
Doctor, can we use KVL or KCL by our choice, or are we going to be restricted on one method?
You can use whatever method you want to use. However, we recommend KCL in this course because usually the circuits we deal with are easier to deal with using KCL. Feel free to
Alright.
use KVL, but here, how many loops do you have? Good
Yeah,
luck.
yeah.
Yeah,
All right, thank you.
no problem. Okay, 3 minutes is up, so let me take a quick poll. I was able to do it, not able to do it, not sure, I have questions. Please pick whatever one you want to pick. By the way, all of these polls, I don't look who answered what. It's just for me to improve how I'm teaching this course. Okay, for those of you who chose not able to do it, what are the sources of difficulty? Why not? What was difficult? Yes, somebody raised his hand. Raise his hand. What were the sources of difficulty? Okay, no questions. Okay, let's go through it one by one. So we had 3 nodes, and this is the ground. So for the first one, you really have a current going out plus a current, through the resistor R1, current going through the capacitor C1, plus a current going through R2. So I use KCL and I have the following equation. I just sum all of them. So assuming 0 initial condition, this is what we get. Okay. Now we have another node. Okay, what was the other node? Let me go back. So this is the other node. So the current here plus the current here plus the current here is equal to the current coming from R2. So let's take it one by one. So we have the current from R2, R1, sorry. No, actually, we're still in the same node. Yeah, we did not move to the next one. Okay. We have here. So we have a current coming out through R2, which is E naught minus EA. Then we have a current through the capacitor, through the inductor, which is IL evaluated as 0 plus 1 over the integral of E naught x, the voltage across the inductor. Then we have a current through the capacitor, which is C2 E naught dot. Then we have a current through the resistor, which is E naught over R3. So this is another equation that we have. So if we write everything next to each other, then we have 2 equations describing the system dynamics. Okay, and we need to, and these 2 equations capture the relationship between the input and the output. We can also take a next step further and differentiate both terms, both equations, and rearrange the terms to eliminate the integral elements and the constant. Because this is not a full differential equation. In a differential equation, I cannot have an integral, so I need to take the derivative of both equations. Okay, this way, this constant will disappear, and this 1 over L E naught will simply become, if I take the derivative, it will become 1 over L E naught of x of t. Okay, so we have 2 equations describing the system dynamics, and they are differential equations after you take the, so this is a differential equation already. You don't need to take derivatives further. For this one, you need to take derivatives. Why? Because you have an integral element and you want to get rid of the constant. This is just to make it cleaner and easier to deal with, and it becomes a well-defined differential equation. Any questions? Okay, we will move to the next step. By the way, if you go to the handout, so I will refer you to the handout after this point. Go to the handout 2, and you will see the next steps there. I want you just to do this as a small exercise. Okay, there you will see more, let's say, simplifications until you get a differential equation. There is only a function of the output voltage and the input voltage. Do you want us to do this on the board? I mean, on the screen now virtually? Or shall we move to the next example? Because if I tell you I need a differential equation, then it needs to be in terms of the input and the output. Okay? All right, since nobody expressed an opinion, so we'll keep going. And then later, maybe we come back to it. Okay, please grab a piece of paper. And we have the following example. Please solve it. I will write down or wait, maybe let me try to figure out a way to share with you the other slide in parallel to this one. Let me see what I can do. Okay, just give me 1 second. I will update my slide real quick. And yeah, so we have these. These are all the things that you need. Let me just put it over here for you to use. Okay. All right. So these are all the, yes, Faisal.
Sorry, doctor, but can you please repeat how can we define the nodes that we have that we need to consider?
Okay, good. So you check how many, let's say, so you check how many nodes at which you can apply KCL, right? So in this case, you have one here, right? So where can you apply KCL in a meaningful way that captures certain relationships? You can do that here, or you can do that here, right? These are the two possible places. You can still do KCL here, but it will just add a small equation, and it will not be that, let's say, beneficial. Okay. Actually, in this example,
Yeah.
I think even this one would be enough, just one node.
What
Why?
about
Because
L and R2?
L and R. Okay, so KCL here, technically you apply KCL because the thing is the current that goes out from here is the current that travels through the conductor and travels through the resistor here, right? So this is the current that you're considering. So this is a node, if you want to consider it as a node, but I mean, it's one of these simple nodes in which you don't really express a separate equation for it, because after all, it will get simplified. So you can just consider it like that. And it's automatic, because if you want to study the current here between R3 and the inductor and the resistor here, R2, directly need to study the two currents over here.
So you mean the current that goes into L and R2 is the summation of the current that coming in, right? That's why we
Yes.
don't consider it.
Yes. So really what happens is that you have one node. So notice the reason I'm saying one node is that here I have a voltage source, right? So you go from the node until the ground. So, I mean, if you take this as, you can still consider this as a node, but it will not be, I don't think it will be that beneficial. So what you can do is just, this node, I think it will be enough. And it will give you a bunch of currents that you need to deal with, right? So you have a current here, and this current is split through L and R2, and you have a current here, R3, and you have a current here on R1, traveling through R1, and a current through the capacitor. And the voltage here is simply, notice, this is the ground, right? So the voltage here is not E2. The voltage here is, let me write it in another color. Let me use red. The blue. The voltage here is E2 plus E0. Okay. Mazen, you still want to say something?
Yes. E2. Why do we write it as a function of t? Is it like I don't remember what it's called, but is it I forgot what it's called. Why do we write it as a
DC?
function of t? That's
You're thinking as DC?
yeah. DC and AC. Why is it like
Okay.
an AC?
Okay, we're working with we have inductors and capacitors, and these are all AC elements. And in control, we care about functions of time because we capture the dynamics, how the system behaves. If I just use DC, then really there isn't much I can do about the system. I cannot study its behavior with time. So it becomes, let's say, not that useful for us. So what we do is that we care about functions of time, and all voltages, currents, even the displacements, the velocities, the accelerations, all of them are functions of time. And this is why we have a differential equation.
Okay.
And this is why we have all of these derivatives. Okay?
Okay, clear.
Okay. All right. So I'll give you, let's say, 5 minutes to solve this example on your own, and then we will discuss how to solve it together. If you have questions or difficulties, feel free to stop me and ask and say whatever you want to say. So the general goal is to identify the model for all voltage nodes. However, here, because of the nature of the circuits, I mean, you can still have a model for this one, but the result will be this current plus this current is equal to, let's say, the current that travels through this and that, right? So you can just skip that node, in my opinion. You can feel free to write it down. I think you can skip it, and I think if you just consider this node, it will be enough. Okay. So basically, I'm considering this node. Instead of saying I have one current that goes out of this one, call it I1, I will just skip I1 and directly plug in the current through R1 plus the current through C. So yeah, so basically we are doing KCL. Actually, we're doing it here, we're doing it here, and we're doing it here. But because these are, let's say, simple situations, so we just can bring it to the equation that we directly, instead of having 3 equations, I can have 1 equation. You can still do the 3, but if you simplify the system, you will end up with 1. And that one will capture the input and output relationship. Okay? Are you guys done or you need more time? Okay, any questions? Any comments? Were you able to do it? Please just quick poll. Okay. Okay, so looks like we need to do it together on the screen. So let me erase all my pins. So again, there are 3 nodes. This one, there is also one here, there is also one here. But because the current that travels from here to here is simply the sum of these 2, I would just skip this node, okay? Because it doesn't add much to it. Technically, you should do it. But I mean, like for things like this, small examples, you can just skip skip that. And as long as you write it correctly, if you're not comfortable doing this and skipping it, so if you make a mistake in skipping a node, then it's your responsibility really to write it down. But if they say one node that is easy to deal with, like these two, then you can just skip that. So the current through R2 and the current through L is simply this one, right? So I will remove that so we don't have confusion. And also we have one final current is through R3. Okay, so this is the first step. We identified the node we care about. Yes, Mazen.
Doctor, isn't those two nodes exactly the same?
In what sense?
In the sense that they have the same voltage over them.
Which node? The green and the red one?
Yes, the green and red one.
Yeah, you're right. I mean, yeah. So I was referring. So, but in the end, you need KCL to capture this one. I mean, I was trying to capture the relationship through the inductor and the resistor, right? So you still need to use KCL here on the left. This is what I meant. Okay. Okay. But you're right. I mean, the voltage here and are the same. Yeah, I might have misspoken. Yeah, thank you. Okay. So now we have a current here through the inductor, and we use this formula. So let's assume T naught is 0 for simplicity, and let's assume ET naught is equal to I T naught is equal to 0. So we don't need to worry about initial conditions. Okay. Now we did that. So what is the current through the inductor? It's simply, let me use, okay, it's simply 1 over L, the integral from 0 to T of the voltage across the inductor. What is the voltage across the inductor? There is the voltage here minus E1. What is the voltage here? It is E2 plus E0. So it is E2 plus E0 plus, sorry, minus E1 E1 d of x. These are all functions of x. What is the current through R2? Again, it is E2 plus E0, because I take the voltage from here up to the ground. So it's E2 plus E0 minus E1, the voltage here on the left, over R2. Now, what is the current through R3? The current through R3 is E2 plus E0 over R3. What is the current through R1? The current through R1 is E0 over R1. What is the current through the capacitor? The current through the capacitor is here. It is C E0 dot. So I need now to sum all of these 5 currents. So I need to take this one, call it 1, take this 2, call it 2, take the third one, call it 3, take the fourth one, call it 4. Notice that I'm taking all the currents going out of the system so that I can sum them all up, right? This is 5. So we have the following nodal balance. It is 1 plus 2 plus 3 plus 4 plus 5 is equal to 0. And these are all functions of the voltages and their corresponding derivatives. So we have a differential equation after we take the derivative of this guy. Because we still have an integral term here, so you need to take derivatives, and then you will have a differential equation. Any questions? Yes, Hisham.
Doctor, I'm sorry, but I didn't get equation number 1.
Okay. What is the voltage traveling through the inductor?
I think E1 only.
Okay, but is the inductor, so E1 is here, and you need to go to the ground. So you need to go, so the voltage across the inductor is really this one minus this one, right? You need the difference between the two. E1 is a voltage source. The voltage up to this point is E1, but then if the inductor is here, then yes, it's E1, but it's actually here between E1 and E2 plus E0. Does it make sense?
Yes, doctor, thank you.
Okay, so you have that voltage, which is E2 plus E0 minus E1, and you use this formula. This is 0 plus 1 over L, the integral from 0 to t of that voltage. Okay?
Yes, doctor, thank you.
No problem. Okay. Now, to complete the story, let me take the derivative of the equation. Yes, Muhammad.
معلش يا دكتور، أنا للحين مو فاهم إيش سالفة إيش دخل إي زيرو في المعادلة الثانية؟ رقم 2 اللي
Okay.
بالأزرق فاتح، كيف دخلت إي زيرو في الموضوع؟
Okay. What is the voltage on the right of the resistor? Okay. You agree that the voltage across the resistor is this one minus this one, right? With this direction of the current. Do you agree with that?
Yes.
Do you agree on? Okay. Now, what is the voltage here on the right of the resistor?
وين قاعد تأشر بالضبط؟ ما قاعد إنه من كثر الرسومات معاكم، وين قاعد تأشر؟
Okay, what is the voltage to the right of the resistor? Here. This one, the purple one. What is it? What is the voltage here?
To the left.
Yeah, this voltage, what is it? This voltage. Do you see it? The voltage, what is it? What is it? You can call it, let's say, EA. What is EA? It's the voltage from this point up to the ground, right?
Yes.
EA is simply equal to E2 plus E0, right? So the current through the resistor is EA minus E1 over R2. Do you agree with this statement?
Yes.
What is EA? EA is simply E2 plus E0. Then we have minus E1 over R2. Right? Because the voltage here is simply the sum of the voltages on the right up to the ground.
Yes, I get it now. Yes.
Okay.
Thank you.
Any other questions? Okay. So now let's take to the, let me see what time is it. Okay. So let's go to the next step, which is about, so now we have, because we have an integral here, we need to find the derivative so that we have a proper differential equation. So I take the derivative of everything. So the derivative of 1 is simply 1 over L E2 plus E naught minus E1. Because zero initial conditions, so everything else is kept. The derivative of what is 2? The derivative of 2 is simply E2 dot plus E naught dot minus E1 dot. This is over R2. The derivative of 3 is E2 dot plus E naught dot over R3. Now, for 4, the derivative is E naught dot over R1. For 5, it's C E naught double dot. So we have now one equation capturing the input-output relationship of the system. Is it clear? Any questions? Okay. If it is clear, then we can move to the next point. Please, if it's not clear, let me know, because if you understand this, then you pretty much, for this topic, you will be pretty much, you'll be good for whatever we will have next in the course related to this topic. If this is not clear, then this is a very, let's say, important aspect of the course, and usually in exams and these things, you might have a question with a lot of weight in an electrical circuit, and you need to come up with a model. So if it's not clear, let me know now so that we can clarify things and make sure that everyone learns what he needs to learn. Okay, there is no question. There are no questions. Then we have a Norton resistive circuits. We can simplify resistive circuits by replacing the resistors in parallel by a single resistor, or replacing resistors in series by a single resistor. We remember that resistive circuits do not have dynamics, so it's in steady state, and it's a DC system. So this goes back to the question we just had. Why do we have functions of time? I mean, in steady state, you have that DC circuit, but once you care about the dynamics, then you have inductive and capacitive elements. So if I have two resistors in series, then the equivalent resistor is just the summation of the two. If I have three of them in parallel, then 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over R equivalent. Okay. Now, we have also the current divider. So basically, using KCL, we know that I is equal to I1 plus I2. So I1, what is I1? I1 is simply the voltage, which is R2I, right, over R1 plus R2. We also have I2 is simply R1 multiplied by I over R1 plus R2. Let me elaborate more. This is the current. You saw this in the first electric circuit course. So, just 1 second. Yeah. Okay. So what is the voltage here? The voltage here is simply I multiplied by, let's say if I want the voltage here on R1, then I1 multiplied by R1. Similarly, it's equal to I2 multiplied by R2, right? These two are the same. Now, if I play with these numbers a little bit, divide by I2 and then divide by R1, we have the ratio of the currents is equal to the ratio of the resistances. So this is what's called the current divider. Okay? And then another expression we have for this relationship is simply this guy. Basically, I1 equal to R2 multiplied by I over R1 plus R2. Similarly for I2. I'll stop here because time is up, and I'll stay around for a few minutes if you have